Ohayo! Good morning in Japanese is Ohayo! It sounds a little bit like one of the states in the United States of America. Ohayo! 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 It turns out the Japanese begin every single morning by paying tribute to the American state. Ohayo! 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 Anybody got time to be sleeping? Wake up. It's part 4 of data-driven modeling. And last time, we did something really exciting where we took the diffusion reaction equation, and in particular, we considered data of chemical concentration of some species as a function of position and time. And we asked, can we purely use that data that you've collected experimentally to discover a partial differential equation? There is some chemical reaction that gives rise to a source in the partial differential equation, but we don't know what this term is at all. And we asked, can we purely use the data with some kind of physical insight and machine learning to discover what could be a nonlinear PDE? And that's exactly what we considered. Over here, we developed what we called the gray box model, where we have some kind of input, position and time coming in, and ultimately concentration coming out. But it's a gray box, so we have some transparency into what's happening with the conversion or the mapping from position and time over to concentration. We know that the system, based on your physical intuition of your experiments, that it satisfies some kind of transient diffusion reaction system. So we wrote down the mathematical structure of a diffusion reaction system, and we can solve a partial differential equation numerically, which is what we considered last time. Now, the term that we don't know, which is this potentially nonlinear source in the PDE, we relied upon a computer, a neural network, to figure out the mapping between concentration and the unknown rate law. And once we know what the rate law is, you can solve this PDE, and by minimizing the loss of the predicted model concentration from the true training data that you've collected from your experiments, minimizing that loss, we can keep doing this loop until it converges to some well-performing rate equation. And after that, we have a mapping from position and time all the way to concentration. Now, what I wanted to talk about today is completely different from everything we talked about with neural networks, AI, machine learning, and that is regression. And in particular, what's called sparse regression. You've probably already heard of regression. You have a bunch of data points, you're gonna fit a least squares regression to all those data points. So you have some familiarity with what regression means. Sparse is actually the key word here, which we'll go to in a little bit. But for today, let's forget all about machine learning, AI, neural networks, because it doesn't involve any of those. With sparse regression techniques, it can be used independently by itself with nothing to do with neural networks and machine learning. It can be used together, and I will show you that in a little bit later, but sparse regression in and of itself uses the power of linear algebra. It does not by itself leverage neural networks or AI or machine learning or any of that. And actually, it is such a powerful technique because it is so simple and elegant in its concept. And simple and elegant things are widely used because it is so simple to operate. And that's what I wanted to cover today. So let's get started with sparse regression. If you know, based upon your physical insight, that your equation came from a diffusion reaction equation, then you can use your data to isolate the unknown term. For example, we can rewrite this equation like the following, where all I've done here is to bring the diffusion term over to the left-hand side. Notice that I put the subscript true underneath the concentration. And this is where your data would come directly into this expression. So the idea is you have measurements of your concentration as a function of position and time. That means that, hypothetically, we should be able to calculate time derivatives and spatial derivatives of your raw data. So just take your data, which is a gigantic matrix, take derivatives in time and in position, just using finite differencing, and you know your entire left-hand side, it'll just be a gigantic matrix of numbers. Right? You can perform each of these operations on your raw table of numbers. Then what you have is a bunch of numbers on the left-hand side is equal to some unknown function of your concentration. So what it means is that if you have some idea of what your right-hand side is, for example, if you had some library of candidate terms of possible combinations of your concentration in nonlinear forms, then maybe we could just fit the data. Let's write all this down. So we could use our raw data to evaluate directly the derivatives on the left-hand side, both in time and in position. And that's going to produce a gigantic matrix depending on how many measurements and how long your data set is. On the right-hand side, we can then construct a library of potential terms that might be a part of your rate law based upon your physical, biological, chemical intuition about your system. For example, it might be a polynomial, just like that, where I've added the first 4 terms, the constant term, the linear term, quadratic term, cubic term, and so on, to your heart's content. Whatever you think is important for the physics, chemistry, biology of a problem, you include terms up until that order. It might also be sines and cosines or logs that are part of your system. Just like that. So you construct a library, in this case, polynomials, 1, linear C, quadratic C, cubic C, sine, and log. So there's 6, in this particular example, there's 6 potential dependencies of your concentration on the rate law, which is nonlinear. Now, you have a situation where we have all the concentrations over on the right-hand side, which you've measured directly, but you can just have an entire span of your concentration over the range that you've measured. And so you can actually rewrite this right-hand side as a matrix times a vector of your unknown coefficients, A0, A1, A2, A3, B1, and B2. Those are your unknowns. If we can figure out what those weights are, then we've done it. We've figured out what the right-hand side is based upon the residual of the partial differential equation, the time derivative and the diffusion term. And therefore, we can use the power of linear algebra to rewrite this expression so that we can figure out what our unknown weights on the right-hand side are. Just like this. So first, on the left-hand side, what I've done is to take this gigantic matrix of all of your data entries after you differentiate, convert that into just one skinny, long, tall column vector. Okay, just dump the data into a gigantic column vector. And on the right-hand side, I've just rewritten the library of your terms times each of the coefficients in a linear algebra operation. So what I've done is to first put the library of candidate terms over into this gigantic matrix. Remember that each of these entries go all the way along each column. So you have to kind of tilt your head sideways, but this first one has the entire column of 1s along it because that corresponds to your first coefficient A0. Your second one has all of your linear scaling of concentration, and so on. And that's going to multiply a vector of your unknown coefficients, A0, A1, A2, A3, B1, and B2. So let's just perform a linear algebra operation for row number 1. So this very top row of this gigantic library matrix. We have the first entry on the upper left over here. That's going to multiply A0. That's going to be 1 times A0. The second entry is going to be C of the very first top row times A1, C2 times A2, and so forth. And you're going to add up all those terms. So it's going to be this number plus this number plus this number, this number, this. So you're going to add up these 6 numbers, and that's going to equal the first entry over on the left-hand side, right there. Okay? And you're going to just keep repeating that for all the entries inside your data matrix. So you're basically doing a fitting in this step. So let's first clarify what the unknowns and the knowns are. All right, so now what we have here on the left-hand side is a vector of known entries. You know that vector and every entry in that vector because it came from your measurements. You know each of the values in the left-hand side. And by the way, we converted to a column vector at this stage because the spatial and temporal connection doesn't matter at this point. It really doesn't matter where each of the numbers came from and whether it came from a time or a spatial component. It doesn't really matter at this point. A lot of you are probably familiar with this matrix form where you have time along the rows, space along the columns, and you kind of have a spatial organization of what each entry represents. We've broken that spatial and temporal organization by making this into a gigantic column vector because we're doing fitting at this point. It doesn't matter where that concentration came from. It came from some combination of time and position and derivatives, but at this stage, we're just fitting. It doesn't matter where the origin of that was, and therefore we can just make this into a gigantic column vector. You'll see that come up shortly when I show you the actual script. Over on the right-hand side, this library matrix, which I've called A, which is a matrix, so there's 2 lines underneath. It's a gigantic matrix. We also know what that is because you selected what the terms in the library were based upon your physical intuition about the system. And of course, you can create an entire vector of concentration profiles spanning over the ranges that are relevant to your experiment. So you can easily generate each column vector. Generating this gigantic matrix A is pretty easy and it's known. Now on the far right over here, that is an unknown vector of your coefficients, A0 over to B2. So I've called that vector X, and so that's your unknown vector. So you can clearly see here at this stage that this has just turned into a linear regression problem where you have some known matrix A times X is equal to a known vector. So it's AX equal B, which is one of the first things we learned in linear algebra, right? You have a gigantic matrix A times an unknown vector X is equal to B. We could just use the backslash operator or just invert this matrix A over to the left-hand side and solve for all of our coefficients of B on the right-hand side. So the goal behind this approach of regression is to find the unknown vector capital X, which has all of your coefficients in it, because once you know the weights of each coefficient, you know exactly the right kind of combinations of polynomials, sines, and logs to take, such that we can recover our overall rate equation. And we want to figure out those weights such that it fits the best through your data. But there is one major challenge, which is that if you just do straightforward least squares, in other words, A inverse, just take this matrix A inverse, dot it into vector B, output X, sounds like a very easy thing to do. That's least squares. But if you do that alone, if that's the only thing you do, you get what's called overfitting, which is it's going to use every single degree of freedom, A0, A1, A2, A3, B1, B2, in every possible way, such that it'll go through the data the best that it can. But if you were trying to discover and develop a model, and I told you, oh yeah, you're going to need all 6 terms, all the polynomials until the cubic, the sines and logs, to represent whatever catalysis or biophysics or population biology or environmental modeling that you're doing, it would not be a useful model because you have all these terms lying around and it wouldn't be that useful for you. And therefore, that's a situation called overfitting, where now you've taken all the parameters and let it do everything it wants to do such that you have all the terms at the end of the day. The whole point is that the library consists of a bunch of terms that may possibly, potentially, perhaps be important for your dynamics, but you don't want all of them to show up. At the very end, you want very few terms, the sparsest possible form that describes and fits across your data. And so that's where sparsity comes into play. Now, before getting into the sparsity and how we can modify least squares to prevent overfitting and to come up with the fewest number of terms to describe your model that goes through your data, I wanted to first show you the structure of what this actually looks like. It sounds pretty easy when I show it to you on the board. It's actually pretty easy on code too, but I think it helps to actually see it. So let's go over to the screen and I'll show you what each of these matrices look like. All right, so what we have here is a simulated data set. I'm going to use the exact same simulated data set that I used from last time, which is the autocatalysis model, where we have the rate law that's equal to c squared times 1 minus c. Remember, this is a rate law that causes consumption of your chemical species when it's bigger than a value of 1, because when concentration is larger than 1, this turns into a negative, and therefore the rate of reaction becomes an overall negative, and so it'll consume your reactants. But when the concentration drops below 1, it starts to produce that species. So it's an autocatalysis model, nonlinear. It requires cooperation. This is very commonly exhibited in biological systems, in epidemics, in heterogeneous chemical catalysis. It's shown all over the place. And we have an initial condition of a Gaussian distribution peaked at the midpoint of the domain at 0.5, so halfway through the domain, and it has a peak valued at 2 at the largest point. Now we have Neumann boundary conditions. So I wanted to remind you what that data set looks like. So let me just show you an animation. Here I'm plotting the concentration, which are your measurements, as a function of position. And as you can see, early on it starts as a Gaussian with peak 2, width 100, centered at position 0.5. I'm actually going to slow that down by a little bit. There we go. And it consumes when concentration is bigger than 1, so it consumes in the middle, and then it goes down below 1, and it says, oh shoot, I consumed too much. And then now it starts to produce everywhere so that the final steady state goes to 1 all the way across. Let's watch it one more time. There we go. This is the simulated data set solved using that autocatalytic chemical reaction. Okay, so let's keep going and continuing where we off with the rest of the code where we load the data. So what I've done is to solve the partial differential equation under these conditions, generated the gigantic matrix of concentration data. And so that's what's loaded in this matrix data. So let me just evaluate this section. And in fact, I'm just going to keep going evaluate down to here. And I'll explain what's going on in a little bit. So what I've done here is to evaluate the data. So data contains the spatial discretization. That's going to be stored in x vector. We have the temporal discretization in t vector. And here we have C data, which is the entire data matrix contained right here. So this is the 10,000 by 100 data matrix. So each of these rows are a single time, slice in time, and then there are 100 spatial discretization over in the column space, so all the way over to the right-hand side. So this is a 10,000 time points by 100 spatial discretizations. It's a gigantic concentration data matrix that I've now supposed that I've collected experimentally. At this stage, this is all I have access to. Now, I just told you that this came from an underlying autocatalysis rate law, but we don't know that anymore. All we have is this gigantic concentration matrix, and that's all we have, okay? And their corresponding positions in time. So what we're going to do here is to now first define the diffusivity, where we also assume that we know the material property inside the model. And we have first the dimensions inside the C data matrix. This is 10,000 by 100. And this is where I start to actually evaluate the left-hand side of the PDE. So this term is dc dt. So if you come back up to the board, this is this term, partial C true, partial time. We're just taking the data matrix over here in C data, taking the difference of that with their neighbor divided by dt. So this is just finite differencing in time step. So now dc dt contains literally another gigantic matrix, which I'm going to show you right here. There it is. So dc dt is now 9,999 by 100 because, of course, you're taking finite differencing, so you're going to lose one row in time because you always need 2 time points to get one derivative, so you're going to lose one row. But that's fine. It's still a gigantic data entry containing the slope in time. And then over here, I'm just an exact same thing in space. So here I'm calculating the Laplacian, which on the board is right here. I'm calculating this partial squared C true divided by partial x squared. Just literally taking finite difference of my concentration data matrix. So I'm going to define my Laplacian matrix, and I'm just going to take C data and central difference, right? This is the formula for central differencing in position divided by the discretization dx squared. So this is the definition of the second derivative in position. And I'm going to store that into a gigantic matrix, which I've called this variable right here. And just to show you what that looks like, that is right here. So also a gigantic matrix, 9,999 by 100. Okay, so now what we can do is to calculate the difference of those two quantities. So over here on the board, we have dc true dt minus the Laplacian. That's going to be equal to the right-hand side. So that's what we're calculating right here. So RC, which is the entire matrix that hopefully has the rate law hidden in there somewhere, is going to be dc dt, which I just calculated, gigantic matrix, minus another gigantic matrix of the Laplacian. So now RC contains that entire matrix that we calculated directly from the left-hand side of the PDE. Now here, what I'm going to do is to take the entire matrix, RC. So let me just show you what RC looks like. RC is right here. So again, 9,999 by 100, gigantic matrix. So this is everything we've calculated by evaluating the left-hand side by using finite differencing directly on the data. We're going to then convert that into a vector. So that's this step right here. I have this gigantic matrix. I'm going to convert that into a gigantic column vector. This is the B vector on the left-hand side. And to do that in MATLAB, all you have to do is colon of the argument. And therefore, our vec just contains here a gigantic vector, right? So this is a huge vector, just taking all the gigantic matrix elements and just moving it to an entire column vector. So it contains the same data. If I were to just plot this, it contains the exact same data, just looks like that. Okay, and it's not in any particular order. It took the entire first column, went to column number 2, column number 3, and it just concatenate them vertically, right? Because at this stage, we don't really care where the particular entry in the matrix really came from. All that matters is that it was a data point that you collected, that you took the proper derivatives in time and space of. That's all that matters. Now, what we have is we've also created another vector cval over here. So that's the C data. So the C data, remember, was the entire data matrix of concentrations, okay, that you measured. And what we have here is we're taking that data matrix, we're subtracting off the last entry, because once again, when you take finite time difference. You're going to lose one row of your entry because you need 2 time points to get one derivative. And therefore, from 10,000 time points, we're going to get 9,999 instead. And so we're going to take 1 to n minus 1 of that gigantic concentration data, so that now these two are the same size. And we're going to take the entire concentration data and then also put it into an entire vector, which I've called CVec. All right. Now what we're going to do is take that concentration vector that came directly from your data that corresponds to each value inside of this RVec. And we're going to build our library. So here what we have is this matrix theta. I've called it theta in the code, but over here on the board, I've called it A. So we're going to make the A matrix, which is contained right here. So what we have here is the ones of CVec. So this is just an entire vector of ones. Here is the linear term, C. Here is the quadratic term, C squared, C cubic, and I've included a C to the 4th. So what I've included in this particular A matrix, or theta matrix, the library matrix, does not include sine and log C shown here on the board. I've instead just taken a polynomial to degree 4. So I have A0, A1, A2, A3, A4, but no sine and log C, because based on my physical intuition, I know that my rate law is going to be of polynomial form. If you didn't know, you might want to add a couple of other terms in there based on your physical insight. But I'm just going to go up to a polynomial of degree 4. That's what I've included over here in the library. And I'm basically ready to evaluate because I've now structured this entire AX equal B form. I have my A matrix, which I've calculated based upon my concentration data. I have my vector of unknowns, which I'm going to need to find right now. And then I've constructed my B vector on the left-hand side. So now this is completely done, which is what I've shown you on the screen. And I can actually even show you what this looks like. So first, let's see, CVec. So CVec looks like, again, in a very, very, very long column vector containing all the concentration data points that you measured from your experiments. And then that's going to be put into the theta matrix, which is right here. So this is the coefficient that we're trying to find. So this is the library of all possible terms. So the entire first column right here just has ones, right? It's ones all the way across, all the way across. It's ones. The second column here is the linear term in concentration. As you can see, it starts at a very, very small value, 10 to the minus 11, and it goes up and it ends at a value of 1. Okay, and then same thing up here. This is C squared, C cubed, C to the 4th. So this is polynomial of degree 4. Okay, so now what we have is everything structured in the right way, and all we need to do now is to do this problem of finding all the coefficients that picks out the right terms from this library matrix. The first thing we can consider is this technique called lasso. It's a sparse regression technique, and I wanted to explain first what this is back on the board. Lasso. Lasso stands for least absolute shrinkage and selection operator. I actually didn't memorize that. I actually had to look into my notes to see what it stands for. So it's least absolute shrinkage and selection operator. Sometimes people will call it an L1 regularization. Regularization is actually is a term that's used to prevent overfitting. So it's one of the techniques, it's a generic term that's used in a situation where we have a lot of possible terms, but we want the fewest number of them to represent our data. So it prevents overfitting. So now lasso has an interesting combination of two terms. The first term is a least squares term that is just direct backslash operator on MATLAB or just inverting the matrix A on the left-hand side. That's what you've learned from linear algebra. Let's write that term down. Now the first term is something that looks like this. It might look a little bit spooky to you. may not have actually seen it written in this way, but whenever you use the backslash operator, whenever you do A inverse and bring it over to the left-hand side to find your unknown x, this is what you're doing. What you're taking is your vector b on the left-hand side, subtracting it from A matrix times x. You're taking the norm of that, and so the subscript 2 means the 2 norm, which I'll define in a little bit, and we're taking the square. And we want to find the argument x that minimizes this norm. First, let me define what an L2 norm is by showing you an example. The L2 norm is defined in this way. Suppose I have some vector v containing n entries. What you're going to do is take the square root of the sum of each of the entries squared. Okay? Let me show you a specific example. Suppose you had a vector v, which had 3 entries, 3, -4, and 0. The 2 norm would just be the first entry, v of 1, so that's 3, squared, plus the second entry, v sub 2, which is -4, squared, plus the final entry, 0, squared, which in this case would be square root of 25. And so it's measuring the distance from the origin to the end of some vector. Okay, that's basically what it's doing. So this L2 norm is what is least squares normal regression, what you are already familiar with doing. All right, so whenever you do least squares, like the backslash operator in MATLAB, this is what it is minimizing. So it's cycling through all possible values of A0, A1, A2, and so forth, such that when you take that unknown vector times the entire A matrix, subtract it off from B, that distance is minimized. So it's saying, find me the argument of x that minimizes quantity. That, in mathematical language, is written in the following way. It is written in this way: argmin, which is argument of the minimum. Argmin, argument of the minimum. In actual English, it's saying, find me an x that minimizes this argument. Once again, find me a value of x containing the coefficients that minimizes everything inside the curly brackets. Okay? So that's normal least squares, but lasso is different. Lasso has a term, a second term, that prevents overfitting, or doesn't prevent it. It penalizes overfitting. And that overfitting term looks like this. What we do is we add another term, lambda, which is called the weight. Lambda times the 1 norm of the coefficient vector x. And the L1 norm is simply defined as the sum of the absolute values of each of the entries inside that vector. Let's use the exact same example that we have here to show you what the L1 norm looks like. So using the exact same example vector of 3, -4, 0, simply is absolute value of 3 plus absolute value of -4 plus absolute value of 0, which in this case will just be 7. Therefore, you can see the clear difference between the L2 norm, which for the same vector became square root of 25, versus the L1 norm, which produced 7. So it's either 5 or 7. So you can see that the metric of the norm is different depending on L1 or L2. Now, the interesting thing about the L1 norm is that it penalizes overfitting or promotes sparsity. What the L1 norm term does is it promotes sparsity by penalizing the existence of entries inside your coefficient vector. So it's saying, I don't want to carry around all these different entries. I don't want all of these to be filled with numbers because I'm going to add up every entry, take the absolute value, and add them all up. and that's going to be a very big number. In contrast, if this were like 1, 0, 0, 1, then I only have 2 active elements, and therefore the L1 norm would be very tiny because there's only 2 entries or 2 terms inside the entire vector that's actually active. Everything else is 0. And therefore, from a sparsity standpoint, it's a huge victory. Now, sometimes people will call this parsimonious model, or a way to develop, yeah, I think it was parsimonious. I distinctly remember when I was applying to graduate school, we had to take this exam called the GRE. I don't know if it's even required anymore. For example, our department doesn't even take GREs, but back when I was applying, GREs were a requirement. And it's an exam where the English section just had like one word, and it was multiple choice, A, B, C, D, just define this word or find the synonym. And I had on my exam parsimonious. And I was like, whoa, wow, I know what this is. I know what parsimonious is. It is unwilling to spend money or resources. Stingy, frugal is what it meant. So it does kind of fit this. I was like, oh, that's amazing. It's like linear algebra. So it is exactly that. You want to be stingy, you want to be parsimonious, you want to be stingy and frugal and unwilling to spend resources. I don't want to spend all these resources. I just want to spend 1 or 2 of these resources, and I want to keep all of them because I'm stingy and I'm frugal. I want my least squares to be minimized, but I'm also stingy, so I don't want to keep around all these terms. So find me the stingiest, most frugal model that also minimizes this least squares. That's what lasso is in spirit. Okay, let's see what that looks like over in the code. All right, earlier we got to the section of the code where we defined the library matrix right here, and we have our known left-hand side in this case, the B vector. And so now we're ready to do least squares with a regularization. So what we're gonna first try is sparse regression using lasso, which I just explained. So in MATLAB, there's a built-in function called lasso. So here we're putting in the gigantic A matrix, or I've defined here theta, and the entry of the left-hand side. So this on the board, we call it B. This is what we're putting into here. And at the end of the day, we should find our coefficient vector x. So we can evaluate what x is here after we do this sparse regression using lasso. I'm not going to talk so much about these extra parameters. You can tune that a little bit. It has a little bit to do with the weight that I explained here over here on the board, how much you want to penalize the L1 norm compared to the L2 norm. You can put different properties inside this lasso function. And what we're going to do is just take that output of the unknown coefficient matrix, which we now evaluated. So that's doing sparse regression using lasso. And then we're just gonna print the discovered equation on the command window and then plot the true data of the data matrix and the rate vector evaluated from taking derivatives of the concentration data and the predicted value based on sparse regression. And that's it. So as you can see here, compared to the previous video with the gray box and neural network and machine learning, there's none of that here. There's no neural network, no machine learning. This is just linear algebra fitting, sparse fitting. That's all we're doing. Okay, so let me just evaluate this whole script. And here we are. So first, what I'm showing you here is the raw data. So we have is the rate, and over here on the x-axis is concentration. So what we're doing is plotting all the different rates as a function of concentration that we evaluated directly from our data. Notice that this is not using the known rate equation of c squared 1 minus c. We're not using the known rate equation. We don't know what that is. This came directly from taking derivatives of time and space on the left-hand side of the PDE. And for that reason, you can see that there's actually 2 values here. So you can see that over here, for smaller concentrations, there are 2 different sets of data. And that's kind of expected because if you remember what the true data looks like, this is a situation where we had a Gaussian that went down and then went down, and then went back up again. And so it actually passed the lower concentrations twice, and therefore each time it went down and went back up, the derivative calculation is slightly different because we're using finite differencing. We have a finite spatial resolution both in time and space, and therefore it's not surprising that you might get two different estimates for the rate, the residual of the PD on the left-hand side, based on different time and spatial measurements. So you got all these points over here on the left-hand side, which doesn't have to be singular valued, right? So we have all these data, and now we're gonna fit the data to the data based upon the unknown coefficients. What I hear now is a fit of the black data over here on the behind the red dashed line, and the red dashed line is the fit based upon the lasso regression I just showed. So you can see that it goes through the data very well, but if you actually look at the command window at the output, just erase that, it looks something like this. Okay, so it's saying that the discovered rate equation has a linear term c, has a c squared term, c cubed, and a c to the fourth. So it doesn't really capture the true solution. Again, the real solution is c squared 1 minus c cubed. So it should only have c squared, and it should have negative c cubed. That will be the true answer. So what you're finding here is lasso doesn't do a super good job finding the sparsest possible model. Even with that L1 regularization term, you can see that it's not quite sparse enough. It's picking up 4 out of 5 terms present in the equation. And even if you tune some of these parameters, even if you change this to some other value like 0.1, it's still not sparse, right? It's still picking up 4 terms over here. You can see in the command window, it's picking up 4 terms. The fit is still really good, but it's not really giving you a sparse model for your chemical rate equation. We can even keep tuning this. It never quite captures it. Okay, so that's 0.3. This is even going up higher. Let's just do 0.5. So now it's still picking up 4 terms. Let's go even higher. Yeah, so the fit is all pretty decent, but it just never quite fits with the true actual answer. So this is my experience with lasso. It sometimes does well, but oftentimes fails to provide a truly sparse model based upon data. So what I'm going to talk about next is a different type of regression and sparse regression called sequential thresholded least squares. And that approach ends up working much better. So let's talk about that sparse regression next. So sequential thresholded least squares, STLSQ. This is an algorithm that is even more strict and sparse, selective when it comes to identifying a particular model and fitting a regression. So here are the steps. Step 1 is to perform a usual least squares regression using this expression, the 2 norm. So you just take this entire AX equal B matrix structure, find the coefficient vector X that minimizes this error, and now you have a vector of coefficients, A0 all the way. And now step 2 is you're gonna filter out all the values that are below a certain thresholded numerical value. So after step 1, you're gonna get numerical values for these coefficients that correspond to each of your terms in your library. And you're gonna say, oh, some of these entries are small. And in fact, I'm gonna remove that if they are less than some thresholded value of lambda, which you're gonna specify. And once it's less than that value of lambda, you're just gonna set that value equal to 0. And we move on to step 3. Step 3 is to perform a least squares once again after you zeroed out the coefficients that are already smaller than some thresholded value lambda. So you're going to perform this least squared on the non-zero values of your unknown coefficient vector x. So you're going to perform this least squared again, but you only include what's called the active terms, the non-zero terms. Because think about it. You performed step 1, least squares. You have numbers for all 6 of these values. Then you're going to remove some of those entries. Say you're going to remove 3 of those entries because 3 of those coefficients happen to be smaller than some thresholded value. So now those are going to be gone. And so now you're going to refit the data based upon only the 3 other remaining coefficients that were big enough, bigger than lambda. So you're going to redo a least squares fit using only 3 of those coefficients. And you repeat the process again because during the next fit, out of those 3 remaining active coefficients, you might only get 2 left after that because the third one might still be, again, less than lambda. So you're going to repeat step 2 and step 3 over and over again for about 5 to 10 cycles. So you're going to loop over these steps until you're done. And after 5 to 10 cycles, you're going to end up with, hopefully, a very sparse, minimal number of coefficients that are active. That still goes through most of your data based upon least squares. So it's a more aggressive form of lasso where it's more exclusive and selective with the terms that you keep around at the very end. And this is a really clever and nice algorithm that ends up working really, really well. And I'll show you what the actual script looks like. So here over on the screen, here we have sequential thresholded least squares, STLSQ. So it's a function that we just made here where it takes in the library. Okay, so that's a gigantic matrix that I've called A up on the board. And we have the values R, which is the left-hand side, right? That's your data matrix after you take all the derivatives. So I called it B over here on the board. And you have some thresholded value of lambda. That's this cutoff lambda below which the coefficient is set to 0. It's no longer active. And then this is the number of iterations, the loops you do between steps 2 and 3. So step 1 right here, okay? We're going to do just a usual least squares. So the coefficient vector is just theta backslash r. So this is just standard least squares in MATLAB language. And then you enter the loop over here on the board. That's this loop right here. So you've entered this for loop. Now we're going to perform step 2, which is we're going to, after we did that first least squares, that coefficient vector x, the absolute value of that, if it's less than the value of lambda, okay, that's what I'm showing here. You take each of the coefficients, take the absolute value. If it's less than lambda, you remove it. And therefore, that's what I'm doing right here. So you're going to identify all the indices where the entries of your coefficient vector is going to be less than lambda. You set all those equal to 0. That's what we're doing here. Now, next what we're going to do is go back to step 3 and repeat least squares only on the non-zero or the active coefficients of x. So we're going to take all of the indices that are not small. So this little squiggly means not the indices that we just identified. We're going to take those entries only, the active entries of x, and repeat a backslash calculation. So we're still doing ax equal b, but we're only doing it on the entries where it is active. Okay, so now this ends with a for loop, and then it loops over for the total max iteration cycles. So it's an iterative scheme where you do a bunch of least squares over and over again, and each time you check, are there any coefficients that are dead, that are not active, that I can remove? And I'm going to do least squares again, and that way you become sparser and sparser as you do more loops between steps 2 and 3. All right, that is the sequential thresholded least squares. Let's see how that performs on our data. All right, from our script from earlier, what we did after we created the entire gigantic matrix of the library, we fed it into a sparse regression. We used lasso before right here in this code. I'm going to comment that out, and I have activated this script right here, which actually calls the STLSQ algorithm that I just explained to you. So it's going to specify some value of lambda, which I've taken to be 0.05. the max number of iterations. The rule of thumb is 5 to 10 is pretty good. And finally, we're going to call that function that I just showed you with the inputs theta, which is the gigantic library, the left-hand side b, which we know, lambda, which is the cutoff, and the max number of iterations. And that's going to produce, hopefully, a sparse number of coefficients that we're going to need to fit our overall data. So let's try seeing this evaluated and see what it looks like. OK. So once again, what I'm plotting here in black is the rate as a function of concentration taken directly from the data sets. I showed you that peak, go down, and go back up. That's the raw data set. I've taken time derivatives, spatial Laplacians. I calculated directly this right-hand side. That's what you're seeing right here. This is the raw data set. Now, when we apply that sparse regression, that's what you're seeing in the dashed red line. So you can see that it fits extremely well. And if you actually look at the discovered rate law, it looks like this. So discovered R as some function of c is equal to plus 1.0056 c squared minus 1.0056 c cubed. And that is the right answer. That is precisely the rate law we used that simulated the data set to begin with. Again, we no longer knew what the real answer was because the data set was all we saw, but the actual rate law that we used to produce the simulated data was the second order logistic rate law. So it's c squared 1 minus c, which is exactly what it converged to. So you can see that this algorithm of the sequential thresholded least squares ends up performing much better for this particular case compared to lasso. Now, I want to warn you by saying that that's not always true. This ends up working very effectively in many situations, but that's not always true. There are so many different ways to perform sparse regression. Several different ways that you can perform sparse regression, and it depends on the data set, depends on the functionality, depends on a couple of different factors, more than a couple of different factors. So it's not recommended to just dive to one thing automatically every single time and just trust that. It's good to just try a couple of different sparse regression techniques and see what you get. Clearly, for the data set I'm showing you here, the sparse regression based on sequential thresholded least squares is performing much better. And it's robust to the particular value. You can change this lambda value to an even more gentler cutoff. So for example, 0.3, and it still produces the same fit, right? And it's pretty insensitive to the precise value that you input here. So it performs very robustly over a pretty wide range of lambda for this particular data set. All right, so I hope that explains a little bit about how you can use your raw data set, put in your physical insight about the diffusion reaction model, evaluate all the terms in the equation that you know or you think should be applicable to your system, put all the unknowns on the right-hand side, and just construct a library of possible terms on the right-hand side and just do sparse regression of some kind. In fact, there is a really cool tool developed by Professor Steve Brunton and Nathan Kutz at University of Washington. And they have kind of pioneered a really robust set of sparse regression tools for ODEs and PDEs. They call it SINDY, Sparse Identification of Nonlinear Dynamics, SINDY. And they have used that techniques in a lot of different contexts for ODEs and PDEs. And it's all based on sparse regression. Fundamentally, it avoids the use of a black box. It doesn't require a neural network, machine learning, AI. It uses massive amounts of data, which is becoming increasingly available for science and engineering today, and uses physical insight and sparsity in just the right way so that you can have a very interpretable model. So the main advantage of this type of sparse regression approach is that you end up with a very interpretable model at the end, because all the terms are terms that you already included in the library. So of course they're interpretable because you put those functionalities in there. So it is probably the best way to achieve an interpretable model. Now, I wanted to write down some comments regarding this generic approach and some things that you should watch out for. So you just saw sparse regression as a very powerful tool that spot on got the right answer for the second order logistic rate law purely from concentration data. And as you saw, it had no neural network, no AI, no machine learning, none of that fancy stuff, just linear algebra and least squares, creative least squares. That's all we did. Couple of comments. Number one, you kind of have to know the answer. What do I mean by that? When you constructed your library of possible terms, we used our physical insight and said, oh, it's probably going to be a polynomial. So I've included polynomial of degree 3 or 4, and maybe it has a sine in there or a log term in there. That's purely based on your knowledge of the system. That's what I mean by kinda. You don't need to exactly spot on know the answer. You don't need to know it's going to have a linear term, a cubic term, a sine, and then a log term. You don't have to be spot on. If you knew the answer, why are we even doing this, right? But you kind of have to know the answer because you have to have a guess of what terms should even be included in the library. So if you have no idea what your dynamics are like, you're working on some super complicated material or a system or a very nonlinear dynamical model where you don't have an idea of what the library term should even look like. For example, what if there's a term that looks like c log c, or sine times log, or any nonlinear combination of a bunch of different terms? You have no idea. C to the cube log c. If that was an important part of your dynamics, if you didn't include that in your library, you are going down a completely wrong path. Because if your answer is not in your library, you are done. You're never going to get the right answer because the search space is confined to the terms inside your library. So if your answer is not inside your library, it's never going to get the right answer. So you kind of have to know the answer. That's really one thing that is important for you to think about. But if you do know what term should be in there, it's incredibly powerful because like you saw, it's so simple of a concept, and that makes it widely applicable and so useful as an approach. So if you know your dynamics, for example, we do in our case, we have an accumulation term, a diffusion term. We know the dynamics must include those terms. And then, therefore, on the right-hand side, we said, okay, well, our rate law is probably going to be some kind of polynomial. And so then you would guess the polynomial terms on the right-hand side, and then we got the right answer. So if you know what the mechanism is, then it's a very powerful tool. Okay, comment number 2. Comment number 2 is a big one for you to remember. You need very clean data. Your experiments, your simulations, whatever data set, measurement that you're making must be resolved spatially and temporally, and it needs to be clean. There's actually 3 subpoints all right underneath this. In our simulated data set, we solved a deterministic partial differential equation with no noise. So we had were data points, for example, concentration as a function of position, that looks something like this. And we took derivatives of those discrete data points, just like that. Because on the left-hand side of this equation, we took our data set, C true, took a time derivative and a second spatial derivative. So we're taking finite differencing between individual points and just drawing lines between them with the assumption and hope that the true data set looks like a smooth curve that goes through all of these points. and therefore it worked out fine. But in reality, in any experiment, any particle-based simulation that you perform, you're going to have noise. And therefore, these 4 data points aren't going to look like this. It's going to have noise to them. So your real data set might look something like this. Therefore, when you try to differentiate these points, what you're going to get is something that looks more like that. You're going to get something that's very jagged because you are differentiating points. And even with a little bit of noise, you're going to be differentiating. And therefore, the slope as a function of position might look something more like this. So even with a little bit of noise, if you differentiate noise that goes up and down, what you're going to get is a rapidly varying derivative. So this is actually the derivative of the position at each of those points. And of course, on the left-hand side, we're taking the Laplacian, which is another derivative of this. So it's actually worse than that. It's taking the curvature. So if you have noise, even with a little bit of noise spatially, you're actually taking the curvature of that, which is going to be amplifying the noise even more. And of course, you're going to be doing that in time as well. So what's very important is for you to have extremely good spatial and temporal accuracy and averages of your measurements for you to be able to confidently draw a slope around each of those discrete points and hope that the finite differencing is actually capturing the true slopes at each of those points in time and both in position. Let me show you an example of how even just a little bit of noise can completely ruin this approach of evaluating terms on the left-hand side and trying to come up with a data matrix on the left-hand side. All right, over here on the screen, what I've done is to generate simulated data sets, but added a little bit of noise to that. So here is the data matrix that was from earlier, the same Gaussian profile that goes down and goes back up. What I've done to that data set over here is to add a little bit of Gaussian noise, just a small amount, okay, 0.01 times some random number generator. And therefore, let me just show you the plot of the actual concentration profile as a function of position and time. So here is the same data set I showed you earlier in black of concentration as a function of position at different time points, shown here. And the black curve is what we saw earlier, the clean simulated data set. And the dashed blue line is the one with added noise. Let me just show you that again. You might not even be able to catch the difference. You can see small ripples in there. The first time I played it, you may have just totally missed that I did anything different from earlier. You can actually see a little bit of these ripples. And let me just zoom into this plot so you can actually see it. All right, so now we're actually seeing the differences. So the black line is the true clean deterministic data set. And these dashed blue lines are the added noise data. So you can see there's a little bit of noise throughout the entire curve, but it's actually not that bad. Right? You see some ripples here and there, but the noise is not that big. In fact, if one of my researchers in my lab collected this blue line from some biophysics experiment or a complex material, I would be like, amazing! Oh my gosh, how did you generate that data? It's so clean. It's such a good data set. That's what I would say, because that dashed blue line looks pretty spot on. And so that's actually would be considered a very good data set. All right, so then now let's try the sparse regression on that added noise data set using the exact same regression that I showed you earlier that worked so well. Okay, so this is a sparse regression based on sequential thresholding, least squares. I've used the same parameters, so it's the same generation of the theta library, the left-hand side, everything, same lambda value, same max iteration, same algorithm for sparse regression. Okay, the only difference is over here on the board. Now C true on the left-hand side is now the one with added noise. The small little blue ripples that you saw, that's what I'm evaluating on the left-hand side. Everything else, identical. Okay, so now I'm going to evaluate this, and you just get garbage. I mean, look at this. This rate as a function of concentration is all over the place. I mean, you can't even see a trend anymore. The black points are the evaluated points from the left-hand side of this equation with added noise. And the reason why it's all over the place is because you're taking derivatives of each of those points in space and in time with noise. And therefore, you're taking differences over a small spatial region, and therefore, your derivatives are going to be super, super jagged because you have a refined mesh. And even if you move the concentration just a little bit, off by a little bit, the slope of that error is going to be huge. And therefore, whenever you evaluate this left-hand side, you're just going to be measuring slopes of noises. And now, of course, if you're trying to fit across this messy data, the regression is not going to work well at all, right? If you try to fit this thing, you just get a bogus fit, right? That's what's shown in red. It's just trying to fit through noise. So you can see that the so-called discovered model has every single term in it. One, linear, parabolic, cubic, quintic. It has all the terms in my library because the generated data set matrix on the left-hand side is just fitting through noise. And remember, I just showed you the concentration profile. It wasn't that bad. The noise was not that bad, but that's all it took because differentiation amplifies noises in crazy ways. That's one thing to watch out for. Let's move on to the second thing regarding having clean data sets. It's very important in sparse regression techniques to have very good temporal and spatial resolution of your measurements. For example, let's draw a concentration as a function of position. And of course, in any real measurement, you're going to have a finite discretization of your measurement, both in position and in time. For example, the spatial discretization of your data may look something like this. And when you take derivatives based upon this data set, you are hoping that the true phenomena look something like this. That it is smooth and doesn't do anything crazy in between your measurement points. So while those points are your actual measurements, the real phenomena might look something more like this. It still goes through all 5 of those points, but it's doing a lot of things in between each of those 5 points that you're not capturing in your finite discretization of your spatial position. So you are undersampling the dynamics in your actual problem. This is a very common situation in microscopy. There are a lot of measurements that you can make from taking a very good picture of a microscopic sample, but no matter how good of a microscope you have, for conventional microscopes, you have a spatial resolution limit of about 100 nanometers, which means if I have 2 fluorophores located 100 nanometers away, if they're within that distance, I can't differentiate the spatial localization of those 2 fluorophores. It's called the diffraction limit. So if I have 2 fluorophores less than 100 nanometers apart, this looks like one Gaussian blur because those 2 point spread functions, which are called, will just merge into each other and you can't differentiate them. But from a biology standpoint, 100 nanometers is humongous. There's a lot of dynamics that happens beneath 100 nanometers. So your spatial resolution of these 5 dots, their spacing will at best be 100 nanometers. But there could be a lot of biology that you're missing within 100 nanometers. So you can't really assume that you know what's happening between each of those points because 100 nanometers is huge and a lot could be happening in between those points. You're undersampling the true dynamics. You might be undersampling the true dynamics in your actual cell. Okay, well, there are advanced microscopy techniques like STED microscopy, STORM, palm microscopy, which can actually get you to a smaller size, to about 10 nanometers, which is extremely, extremely good, but a lot of those techniques, if not all of them, have very poor temporal resolution. You usually have to fix your sample with formaldehyde. You have to use a special combination of dyes that are very carefully labeled. It must be temporally very, very, very slow, such that you can take a scan across your sample and illuminate one fluorophore at a time, or do all these tricks so that you get amazing spatial resolution, but you lose dramatically on temporal resolution. So a lot of problems are both fast and small. And if you want to capture those dynamics, you have to have a balance of having good temporal resolution and spatial resolution, because whenever you're solving a PDE like this, you're going to have dynamics. The left-hand side, dc dt, time, means that you need good temporal resolution. And if whatever you're measuring is not fast enough to resolve all the dynamics, then this technique is probably not going to work so well. In contrast, for both A and B, that approach I talked about last time, where you have the gray box, the neural network, you're solving a PDE, you are much more likely to come up with a smooth concentration profile that will actually go through not necessarily your points, but it'll be smoothly going through space because you're actually solving a PDE. You're solving the full equation. You're minimizing over the full time and spatial trajectory. So you're much more likely going to converge upon at least a smoother thing that minimizes the overall error. And you're going to be less sensitive to small bits of noise or the lack of temporal and spatial resolution. So like I said, these types of data-driven models are all different tool sets. You shouldn't just be married to one and just use that all the time for all of your experimental measurements. It's just good to know all these different techniques so you know when you can use certain ones, when you do them, when you can trust them, and it's good to know. So depending on the situation, the other technique I showed you earlier where you use a neural network, machine learning, that may perform better in certain situations. Okay, let's keep going to the third point underneath this clean data point. So the last point I wanted to talk about with regarding data is that this type of approach gets a local point-wise estimate of your unknown function, and that may miss global dynamics. Let me make this concrete. Let's suppose you have a concentration profile as a function of position, and you measured data at these values shown in the dots. And it's very clean over most of the space, except there's a region inside there which is very noisy. And whenever you try to do a sparse regression technique over data sets that look like this, even if your noisy range is very narrow and small compared to the overall clean dynamics, this small bit of noisy region could actually contaminate the fit across the entire global dynamics. Therefore, local point-wise evaluation of a locally noisy region could actually miss the overall global dynamics of your actual fit. So these are the three different things you should at least think about when you apply or try to apply this type of sparse regression technique. Now, like I said, there are many users of this approach of sparse regression. I actually use it a lot as well. It's extremely effective. And you just have to watch out for a couple of different things related to your data and your intuition regarding your problem. And there's actually a lot of methods that you can use to smooth out noise and improve your temporal and spatial resolution by doing some kind of clever tricks and techniques. But a lot of that is just kind of feel and trial and error. So you can do different types of filtering approaches to remove noise so you can get better differentiation, time derivatives and spatial derivatives of your raw data set with noise. And there's a lot of tricks you can play. But in general, sparse regression as an overarching rule of thumb requires very clean data sets. And this is where I think it's very exciting and interesting is that 10, 20 years ago, it was really hard to get clean data for a lot of phenomena and materials in science and engineering. We were limited by good measurements, having a good microscope, having a good telescope, having a good material science measurement, whatever it may mean. Experiments, apparatuses, instruments have improved so much with numerical computation also advancing significantly. We're living in a data-rich environment where now having clean data is a little bit easier, maybe way easier than it was 10 to 20 years ago. So that's where this type of sparse regression technique has become increasingly more popular, because it turns out that the data oftentimes are clean enough to be able to do such a simple thing like this. No AI, no neural network, no machine learning, just linear algebra. Sparse linear algebra. That's all we're doing right here. And it's popular because it works so well and it's so simple. All right, let me just do one final thing of trying to combine what we discussed in the last video, where we have the gray box, the neural network for some unknown function, a source, the chemical reaction. And at the end, we trained a somewhat reasonable black box for input of C, spitting out the reaction rate law. So now I was wondering if we can combine sparse regression after that to make our black box neural network a little bit more interpretable. So over here on the code, what I'm doing is I am loading the solution from what we obtained from the black box, gray box from last time. So we have here is, I'm just setting up the Python environment. Right there, I am loading the solution that I saved coming out from the neural network approach. And I'm going to store it inside these vectors and matrices as outputs. And so now what I have is those become the data that we're going to fit on sparse regression. So C prediction is the predicted concentration profile coming from the neural network model that we trained using the concentration. The raw data, we trained it. Now we have a black box neural network for that element. And that's what C prediction contains. And then now we're going to use those weights based upon the neural network parameters. And now we have the rates as a function of the concentration from the gray box model. And I'm going to apply the exact same sequential threshold least squares with the same lambda value of what we just tried. So let me just evaluate this and see if we can use the sparse regression on the neural network model. So here, what I'm going to evaluate, let me just explain. First, this black solid line is the true rate law. That's C squared minus C cubed. The red dashed line, that is the solution from the neural network model that we discussed in the last video. If you recall, at the very end of the last video, we compared the true rate law with the neural network produced rate law, and we're like, oh, it looks pretty good numerically. That's what I'm showing here in red. Now, just to be clear, I'm using the data points in red, not the black. I'm using the red dashed data points and doing a sparse regression on that. So now I'm taking the output from the neural network, doing sparse regression on that to see if I can make that interpretable. Now when I do, I get this green dashed line shown what I call the regression. So that's the sequential threshold least squares. That's what's shown in the green dashed line. And you can see it fits the red dashed line really accurately. Unfortunately, if you look at the command window, the actual discovered equation is not sparse at all. It's actually capturing all the terms inside the polynomial from 1 all the way to degree 4. So it's finding that all the coefficients are all important. So it's not finding a sparse model, unfortunately. Even though the fit is very good, it's not finding a sparse model. We can try cranking this up to a larger thresholded lambda value. So now in that case, we find is that it's gotten a little sparser. So the constant term 1 has disappeared and C to the 4th has disappeared, but it's still not sparse enough and it's not finding the true solution. And we can still keep cranking it up. And it's closer now. So you can see it's found the two terms in the polynomial that is the correct answer, C squared and C cubed. And it's almost correct. This coefficient should be 1 and -1 instead of 0.9 and -0.95. So it's getting closer. I'm not sure how much more we can push it. So now I think it's not changing anymore. I think at this stage it's finding those two terms inside the polynomial, and the numeric values are hanging around at around 0.9 and 0.95. So it's almost the right answer, not quite. the fit looks about the same. It's actually closer to the black curve. And the only reason why it's doing that is because I'm setting the lambda threshold to be so high that it's removing a lot of the terms. It's actually forcing it to be sparse in kind of a very aggressive way. And so that's why it's converging to these two polynomials. But I wouldn't say this is a super robust fit. I mean, this lambda value seems kind of arbitrary. And if I use the smaller value that I used for the true data that I used with the smooth derivatives and the spatial derivatives like I showed you earlier in this video, that value spot on matched the right data, whereas this time it's not sparse at all. So this is, I think, highlighting the challenge and the difficulty of these types of data-driven models. It can be kind of finicky. If you just saw this, if you just saw the red dashed line compared to the black curve, you'd say, oh yeah, the neural network found a pretty good black box model that takes in concentration and spits out a rate law. But if you use those values and try to do sparse regression to make that interpretable, then it's not working so well. So here's a situation where I would not take this step and try to make it truly interpretable because it's not really robust. It's finicky. If I change the sparsity cutoff value, it's giving different results, and I don't know how much I would trust this result, especially if you didn't know the right answer. In this case, we're using a simulated data set. We know the answer, and that's why we're able to nudge it in the right direction. But in real life, in a real experiment, there's no way. You would have no guidance on what number to choose as your threshold. And so this is the difficulty. The gray box neural network approach works really well. As you saw last time, it finds the right unknown term, it puts in the right physics, it puts in the constraints, and you can get a pretty good model. But trying to make that black box element more interpretable by doing a sparse regression after that may work sometimes, but I think it's pretty tricky. Of course, you can work with this. You can try to play some tricks and refine your library, and you can play some games, but it's not super robust in combining the two techniques one after another. Maybe there are some clever ways to do that more robustly, but at least with my very simple-minded, educational, spirited code, it's not capturing it that easily. Great. Let's finally end with a recommendation of what approach you should take and how you should apply the two different approaches. In summary, what we talked about today is if you have a clean data set that is highly resolved in space and time, then you can differentiate very cleanly. And if you also kind of know the dynamics such that you can create an intelligent library that captures all possible terms inside your system, material, or phenomena, then sparse regression works extremely well. In contrast, if your data are noisy or you have limited access to the dynamics in your data spatially or temporally, and or you have limited knowledge about the dynamics such that you can't come up with an intelligent number of terms inside your candidate library, then the approach we talked about in the last video where you have a neural network, you have a PDE solution, you mix in physics-based structure plus a term that you don't know, that you rely upon a computer to help you with training, that may be a better approach. And if you think back to what we talked about today, this sparse regression technique does not involve that you solve an actual PDE. Did you realize that? Last lecture, we actually had to time step Euler forward integration of a partial differential equation, and it was complicated. We actually had to go into a Python code, do gradient descent optimization. It was extremely complicated, and it was not as interpretable at the very end as I just showed you with the rate equation and the rate law. That wasn't super interpretable at the very end. Therefore, this approach on the bottom is definitely harder, it's much more involved. So Definitely, if sparse regression, you can get by with that, I would recommend it because it's much easier to develop a model based on sparse regression. And if you're on the bottom, although you may have more robustness or consistency, it's generally going to be a harder approach to implement. And the major pro of sparse regression is that you're going to have a higher chance of interpretability of the resulting model because you've only put into the problem, or you constrained it using terms that are in the library. It's never going to find a term that you didn't put inside your library. Therefore, if you kind of know the dynamics, you know what terms to put in your library, you're going to get a much higher interpretability of your resulting model. So this all comes down to a balance. As a scientist and engineer, you have to think about how clean your data set is, how spatially and temporally resolved it is, how much do you know about your dynamics, how much do you know about the unknown term in your equation. And there you have to think about what combination of different tools should I apply to develop the best possible partial differential equation, or ODE, or any model that you want to use to predict a mechanism or develop a theory for your complex material, complex system, or phenomena. All right, that's it for what I wanted to talk about with sparse regression. Next time, we'll talk about a completely different subject. See you next time. Bye.